Welcome back. So far we have done many attributes of the system of particles and dealt with rotational motion, defined many things, but still we are lacking something which is quite important, and I address that to you, and that is moment of inertia, which is an analog of mass in rotational motion. Can write it as capital I normally. Analog of mass. So analog in Hindi Urdu is a pattidar, a badal. Is what is mass in general and the role it plays in determining the kinetic energy, etc. Like I'll come to that. Half mv square, force is equal to ma, etc., etc., where the attribute of mass is defined and we have to understand that. Similarly, in the case of rotational motion, we have moment of inertia. And to understand moment of inertia, we will take a very simple case where we consider a uniform angular rotatory motion about a fixed axis. The axis is fixed, so we are confining ourselves to certain things, that the motion is uniform, having moves, each particle moves the same distance in translational motion, equal intervals of time, and the rotational motion has the same angular velocity in equal and moves the same angle in equal intervals of time. So there is a question which we address: what is the kinetic energy of a rotating body? To address that, let us recall that in case there is a body which is undergoing circular motion, a body of mass m undergoing circular motion with uniform angular velocity, and the speed of the body is also the same. It is having a radius in which it takes place, which we are taking as small r. Then we define V is equal to omega r, so that for the ith particle I can write Vi is equal to omega Ri. Simple, no problem. So if we describe the kinetic energy of this particle or kinetic energy of this mass, then we define, like we have done before, that the kinetic energy Ki associated to the ith particle is equal to half the mass of the particle into the velocity square, Vi square. And using this relation, Vi is equal to omega Ri, I just substituted that this will become equal to half Mi, which is the mass of the particle, Ri omega whole square, which turns out to be equal to Ri square omega square. And therefore, the total kinetic energy of the system of particles that we are dealing with, that will turn out to be equal to the summation of all these particles from I is equal to 1 to n Ki, which I am obliged to write here as half summation mi Ri square omega square. And what we do is we just rearrange the terms, half sigma of I to n mi ri square, total this multiplied by omega square. Remember, omega is constant for a rotating body. This is about a fixed axis, etc., etc. So from here I define this quantity in this relation as moment of inertia. So the moment of inertia, which is the analog of mass in rotational motion, is defined as I, capital I, always is equal to sigma this mi ri square. Okay, sigma I ri square, which I am writing here also, just to for your recollection. Okay, so this equation gives us the definition of moment of inertia. It's a very simple proposition. So the kinetic energy associated with that set of particles is equal to half I omega square. Just like if the total mass of the system of particles is m and the velocity associated is v, then I can write k is equal to half mv square. This is similar relationship, half I omega square and half mv square for translational motion. This is for rotational motion. Now, I have defined this, then I must make one thing clear. You increase the omega, you decrease the omega, you do anything with the omega, the I is not going to depend on omega. So it is independent of omega. So what is it going to depend on? It depends upon the characteristics of the body, the composition of the body, the spread of the body, the definition of the body, and of course, one of the most important things is that we must define the axis of rotation. So we can do that. We can calculate it for some simple bodies. The moment of inertia, for example of a ring, for example of a rod which is rotating about one axis or the other, for example about the diameter of a ring, etc., etc., which we follow suit. So to elaborate on the definition, we'll just consider a few cases where we'll calculate the moment of inertia about axes. Okay, so in the first case, I take a thin ring of mass m, where the mass is uniformly distributed all over the ring. Okay, and the radius is the same for all over the ring, and it is rotating in its own plane. Okay, it's rotating in its own plane about an axis which passes through its center, which incidentally also is the center of mass and center of gravity, whatever you want to call that. So this axis is perpendicular to where the to the plane in which the rotation of the ring is taking place. Very simple example. I have shown it here. It's a counterclockwise, anti-clockwise rotation. I'll just consider a small mass dm or whatever you want to say, and then our mass per unit length of the circumference we can take. Okay, and then we can integrate over the whole circumference to obtain the mass capital M of the ring. But I just say that the kinetic energy of this, because everywhere the velocity is v square, this is equal to half mv square, which is equal to half m r square omega square. because V is equal to R omega. So this turns out to be equal to half I omega square. So therefore it will be equal to mr square. Well, ahead we'll come across the perpendicular axis theorem and the parallel axis theorem, etc. So making an application, I can have a different choice of the rotational axis. And if the rotational axis is along a diameter, then the moment of inertia becomes half the moment of inertia which has been obtained over. So it is half mr square. If I have an axis in its plane which is at one of the ends and this whole body is rotating about this axis, then there will be other means to calculate the moment of inertia. So next we go to another case. So another simple example, very easy, nutshell, is for determining the moment of inertia of pair of equal masses m by 2 and m by 2 about the center of a massless rod joining the two masses with the axis of rotation being perpendicular to the plane. What basically is required is to understand this and then make a sketch accordingly. So I have made the sketch over here, simple sketch, where I have the axis, I have the masses, and this rod is massless as per our consideration. So this mass is n by 2, n by 2, l by 2, l by 2 are the distances. Now since I can add up for the moment of inertia of this plus the moment of inertia of this about the same axis will be the moment of inertia of the whole body. And then I can calculate in this very simple situation that I is equal to m by 2 into l by 2 whole square plus the same repeat for the other end m by 2 into l by 2 whole square, which turns out to be equal to ml square by 8 plus ml square by 8, which is ml square by 4. So again a very simple example, that of a thin rod, homogeneous and having the same density all over, about a perpendicular axis, which I have shown here, passing through its midpoint, which will also be its center of mass, as also you can say its center of gravity. So I have just sketched the rod of length L by 2 plus L by 2, this total length is L, and through the center I have this axis about which this is rotating. Okay, the total mass is equal to m and the total length is equal to capital L. Now what I do is I take an element of mass, and this length over here is very small, this is dx, and it is situated from here to the center at a separation of x. So look here, this mass becomes equal to the mass per unit length multiplied by dx, and x is the distance from the axis, and which I have shown here, that the mass per unit length is taken as small m is equal to m upon L. So the moment of inertia can be defined as the integral of the mass per unit length into x square into dx. So it's simple. So I use the integration that x to the power of n is equal to x to the power of n plus 1 divided by n plus 1, of course provided n plus 1 is not equal to 0, so that this quantity becomes infinite. So using this relation, which we have been using time and again, I can see that m is a constant and the integration turns out to be equal to x to the power 2 plus 1 divided by 2 plus 1 is x cubed by 3. And when we substitute the limits, minus L by 2, this end, this is minus L by 2, because we are going in this direction, and then plus L by 2 to L by 2 to take the whole body under consideration. Then we find this as ml cube divided by 24 minus ml cube, minus into minus, and that makes it plus. Okay, so this turns out to be equal to ml cube divided by 12. I am just separating ml separately because this will give you the entire mass of the rod under consideration, and this will turn out to be equal to ml square by 12. Now, with the same kind of a setup, I can give you in number 4. The thin rod of length L about a perpendicular axis passing through its, not the midpoint, but instead an end point, its end point. So we are shifting the axis. We are shifting the axis from here to here. I am shifting the axis from here to here. And then my rod goes around an axis which is like this. This is the axis, my thumb, and the rod is going like this. It's very simple. Then in the same situation, what we'll do is same kind of thing. I'll shift from here, and my distance x will now count from here to here. So dx will be there, and I can write from 0 to L. Okay, so this integration will be from 0 to L, mx from 0 over here, and L over here. So I get the same thing, mx square dx. Of course, x now in this case becomes from here to the point under consideration over here. Okay, so this is the 0 end, and this is the end with L. So I can go and integrate this from mx square dx, mx cube. From here it will be 0 and it will be equal to L. So you can see that in that case this will turn out to be equal to ml square by 3, ml square by 3. The geometry is the same, the rod is the same. The only distinction that we have made, the angular velocity could be any choice. It doesn't matter, because the moment of inertia is independent of the angular velocity of the rotating rod. The only thing is that the axis of rotation has been changed. So with change in the axis of rotation, and this you could have axis of rotation, we could take anywhere, any defined point, and you can be asked that from here to here it is L1, and from here to here it is L2. So total length L becomes equal to L1 to L2, etc., etc. All kinds of complexities, but you should be able to deal with this because you have learned the method how to do it, and you can do it very easily. So the next example, I take a uniform circular disc about an axis perpendicular to it. This is the disc, a uniform circular disc in known geometry, and the axis is passing through its center of mass. The axis is passing through its center of gravity. The axis is passing through its geometrical center over here, perpendicular to the plane containing the circular disc. Now, what I have here on this ring, I draw another ring, very thin one, of thickness dx, which is infinitesimally small, and taking the radius over here as x for the entire thing of mass m and radius r. So first of all, I must know the area of the disk. The area of the disk is pi r square, you know it. Everyone knows. And the circumference is 2 pi r. So the mass per unit area I define as sigma. This I can write as m upon pi r square. Simple. And the area of this ring, this will turn out to be equal to 2 pi x, which is the circumference, multiplied by dx, which is its thickness. It is a kind of a ring within the, and this is also symmetrically situated. So now for the moment of inertia calculation, I build up the case like this, that this becomes equal to 2 pi x into dx multiplied by sigma, which is the mass per unit area. This is the mass of the ring, and we know that because all points on the ring are situated symmetrically about the axis of rotation, therefore I can take this as 2 pi sigma into x square is x cube dx from 0 to capital R to the end. And then I substitute for sigma, which is total mass upon pi r square for here, and then this turns out to be, with the formula that we have, x to the power of 4 divided by 4, and the limits are put there. So we don't need a constant of integration also, because that will cancel out. This is a finite case, we know the limits. Then I write this as 2m upon r square, pi cancels, 2m upon r square into r to the power 4 divided by 4, and when I rearrange the terms, r square goes with r square, and we are left with half m r square as the final value, the result, which is a desired result. Well, you can see that if I have a uniform cylinder and we want to calculate its moment of inertia about this axis, okay, passing through its own axis, okay, geometrical axis, or whatever you want to call, then again we can say that we can cut it into small disks. We can cut it into small disks and integrate it over from this end to this end, and finally the result will again be half mr square. So this is about the axis, one thing. The other thing is that whatever I have built up, similarly I can build up for an annular disk. Suppose there is a disk with an annular kind of aperture. This part is missing. So I can say that this is, the radius is r1 and this radius is r2, and then again work out the same kind of mathematics. The limits now turn out to be from r1 to r2, the two given things, and that is how we can calculate the moment of inertia through this kind of an axis, the defined axis, for the case of annular ring, annular cylinder, etc. And the same kind of mathematics, mathematical tool that we have used is used in all these situations. So it's nothing very tricky about it. Simple kind of mathematics you have to follow, and you can obtain the results of different geometrical shapes. Okay, you can take, for example, I'm not going to do it for all cases. For example, for a shell, okay, for a thin shell, and then you can also show as to what is the moment of inertia in that case, and the shell can be later on, it can be a solid shell, it can be an annular shell, okay, and all kinds of things are there. Of course, when we talk about the theorem of axes, parallel and perpendicular axes, then you know how we can shift this from here to here and calculate things easily. It's one thing. Now next, before indulging into calculations like that for the bodies of geometrical shape for which the calculation can be made easily, I will define to you a general term which is known as the radius of gyration. So now, after doing so many exercises for regular bodies, wherein we have calculated the moment of inertia of several bodies, now in any rotational condition, rotation of any body, regular or irregular, the body has a moment of inertia, which is a fact, and the body has a mass. This is also a fact. So now we define a radius of gyration. This is defined as I is equal to mk square. Okay. So k becomes equal to I upon m under root. K is equal to the moment of inertia which we know, the mass which we know, and that means the axis of rotation, etc., the composition of the body, etc., what we know. Now this is simply, as it appears to us, this k is called the radius of gyration. Of course its unit is meter and its dimensions is L. So we have a system in which we have a mass and there is a rotation, and we define the moment of inertia of the system, calculate or experimentally determine that moment of inertia, and then in a simple manner we put it as I is equal to mk square. So for example, now let us define it. It may be defined as the distance from the axis of rotation. We'll define the axis of rotation, which is important, and there is a distance which we call k, and we consider that the entire mass of the body is concentrated at this point m, which is away from the rotatory axis about which the rotation takes place, by a distance k. So the rotation of a mass point, let me read again, it may be defined as the distance from the axis of rotation of a mass point whose mass equals the mass of the whole body, capital, and whose moment of inertia is equal to the moment of inertia of the body about the defined axis of rotation. Okay, so there's the concept is about a single particle having a mass equal to the mass of the body. The concept is about the moment of inertia that we can calculate, and for example in the case of a rod, about its center, the moment of inertia of the system was equal to ml square by 12. If allow me to write it as by definition, the moment of inertia can also be written in terms of the radius of gyration, mk square, then in this particular case k becomes equal to L upon root 12, which is L root 3 by 6. If you are confused, then I will do that mathematics for you. L upon 12 is L upon 2 into root 3. So I multiply in the numerator by root 3 and in the denominator also. So this becomes 2 into 3 and this turns out to be equal to L root 3 by 6. Okay. Because here the multiplication is easier if you put it in the numerator. How much is root 3? I remember it. Root 3, for example, is equal to 1.732. And in Urdu, Hindi, my language, I remember it as 1732, like under root 2, which is 1414. Okay. So many of these things got to be remembered, and we can substitute the things and make the calculation. So what we have done today, it's nothing. It's moment of inertia has been defined. It has been taken as analog of mass in the rotational motion. I have defined it as from the concepts of kinetic energy. Okay, the moment of inertia has been obtained. So I can write many things if we know the omega value, and the kinetic energy of the system is I omega square. In that case, etc., etc. In many cases I have done it. In many cases I have left to you to do, and I have introduced the radius of gyration. Of course, I have left aside the two theorems, the theorem of perpendicular and the theorem of parallel axes, which I shall describe to you in the next outing. So far, I hope I have enjoyed. I hope you have enjoyed. Thank you very much.